Oh, good morning, everybody. What we're going to be taking a look at is the new large page support in the Z10 processor. And kind of the approach that I want to take is to go ahead and introduce it. Let's put it into context a little bit, try to get a sense of what particular problem it's trying to solve, and then we can take a look at the particular implementation of it in this environment. So basically, with the large page support, what we've got is that we've got something that is a very specific feature that's been implemented. And so it's intended to resolve a special problem which deals with the large storage users. So as a result, a lot of this is considered to be something that we need to look at from the perspective of an application's usage as well as the work pattern that that application uses. So as a result, there's sort of a warning that goes with it saying that it could be detrimental for some applications, although exactly how detrimental is something that still would need to be determined. For the most part, this is going to likely result because of overcommitment of resources rather than that the application itself suffers as a direct result of the large page support. In addition, ZOS does not consider building large pages an immediate priority or an immediate action item when they are requested. So it's entirely possible that you could still end up with a lot of the storage being requested in 4K segments, or 4K pages, I should say. The requirements are that we have a Z10 processor and minimally that we're running ZOS 1.9 with this APAR 08-20902 applied. And this would enable the large page support in this environment. Now, let's kind of take a step back for a minute and consider the context by which this is actually being implemented. And in particular, if we consider back to the early days of the ZOS ancestors, you know, the MS, MVT, MFT type of systems, they were all real storage systems. And as a result, of course, you know, the applications would come in, just allocate the amount of storage that they needed, and proceed to run from there. So there was no special consideration given for accessing memory or the types of things that you needed to do. The applications require contiguous storage, so as a result, the biggest issue that occurred with the real storage implementations was, one, how much could you physically install? And then the second, of course, was the fragmentation issue, so that as storage was being assigned out to applications, when various applications would end, they would leave these holes in storage that could only be filled by programs that required that much or less storage. So over time, you ended up losing access to some of the resources you had installed. Now, the solution was virtual storage. So that virtual storage really addressed two concerns. One was the fact that we could initiate this action called paging, whereby we could keep the oldest pages out on auxiliary storage instead of tying up a physical resource. And then the other was that we could create a virtual map whereby the application saw itself as running in contiguous storage, despite the fact that it could be backed by real storage frames that were scattered all over the place. So as a result, we really ended up with a couple of improvements here, whereby the application could continue to run as if it were running in a contiguous chunk of memory, and at the same time free up some of that real storage by keeping the unreferenced pages, presumably, on disk. Now, the downside was that if we had overcommitted our storage usage, then we would end up having to bring in those pages from disk, and as a result, we would incur the overhead of that. In addition, with the virtual storage, one of the overhead issues was that we had to translate every virtual address into a real address. And so we ended up having to have an additional piece of hardware that would be involved in the address translation, as well as ensuring that the processor could readily resolve these and store that information someplace. And part of that fits into the whole caching architecture that is employed by the hardware. Now, the problem that you end up having in any of these systems, if you kind of watch their evolution, is that initially the systems were relatively slow. So as a result, having access to real memory, was a benefit. But as the demand became for larger and larger applications, then obviously algorithms and architectural changes had to consider how we could work with the physical resources that we had. So virtual storage was a good first step in that we paid a price in terms of overhead for managing it, but at the same time, it allowed us to achieve greater throughput by allowing more applications to coexist and larger applications to be run on those environments. Now, without getting into a whole bunch of extraneous detail, eventually out of this environment, MVS surfaced, and we ended up with a bunch of other architectural changes so that we had the concept of address spaces introduced, which gave all of the applications access to the full range of virtual storage and the other elements that came with it, ultimately data spaces and hyperspaces during the expanded storage area, and now we're up to the memory objects in 64-bit memory. Now, the underlying problem that we keep running into here is that we have different demands that require different solutions from a scalability perspective. And so as the processors get faster, we can put more on them. But as a result of putting more on them, they end up demanding larger and larger amounts of resource in which they can either be stored or which they can gain access to. And so we end up with the scalability issues that start to come up, where an algorithm, for example, that worked well in one environment doesn't work so well as we start to scale it up and we increase the demand on those resources. So this is kind of where we are now with ZOS, because one of the things that we had was that we had an environment whereby we ran for nearly a decade with 16 megabytes as being the maximum that we could use in virtual or real storage. Once MVS XA came along and we introduced 31-bit addressability, we had access to 2 gigabytes. And that gave us a fixed resource pool, essentially, for almost 2.5 to 3 decades. And so at that point, most of the architecture was placed around the limitation that we had in terms of real memory. Now, there were stopgaps where expanded storage was introduced, and things like that, but they were never part of the direct addressability of the application. With ZOS and the advent of 64-bit storage, we suddenly have opened it up to where we can increase the amount of accessible storage, in theory at least, 8 billion times. So as a result, with that kind of scalable growth, we end up in the situation now to where the processors are not going to be able to keep pace speed-wise with the ability to access such a large resource. So we're starting to find that starting at ZOS 1.8, for example, a lot of the traditional management algorithms that were associated with storage are being changed, because we're finding that it's simply taking too long to manage individual pages, for example, or to deal with the conventional algorithms as they were structured. So we're seeing redesign and a reshift. And large page support fits into that same general category. Now, some concepts here is when we're talking about a virtual address, which is the address that all of your programs see, then these have to be converted into a real address or an absolute address at some point. So from this is we're going to have dynamic address translation occur. And then we also have the real address, which is where we have to convert that to an absolute address by prefixing, because its storage is associated with a particular CP. And then the absolute address is the physical location in memory, which is used by the processors and the channel subsystem itself. So conceptually, those are the 3 types of addresses that we're dealing with. And so when we look at this, we want to put this into the general context of the Z10 architecture.